The Indian Association of Structural Engineers, also known as ISTRUCT-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. ISTRUCT-E is registered under the Societies Registration Act 21 of 1860. ISTRUCT-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, ISTRUCT-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar as its president. ISTRUCT-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, ISTRUCT-E has collaboration with various international professional like-minded associations and institutions. ISTRUCT-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. ISTRUCT-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. ISTRUCT-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs, seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements, and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. ISTRUCT-E's activities are widely appreciated and known for quality technical contents. ISTRUCT-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. ISTRUCT-E's publications are becoming popular with time. ISTRUCT-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, ISTRUCT-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. ISTRUCT-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. ISTRUCT-E has its student chapters in several leading engineering institutions as well. Membership of ISTRUCT-E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about ISTRUCT-E is available on its website www.istruct-e.co.in.
Hello, dear friends, my voice is audible?
Yes, sir. Yes, sir.
Hello. See, Dear friends, welcome to this webinar. Today's topic is advanced computer vision techniques for structural health monitoring. The speaker is Dr. T. Jyoti Sharvanan. He graduated uh, way back in 2012 from Guinea Engineering, famous engineering college, and thereafter he did his MTech in 2014 from Structural Engineering Research Center, Chennai. Further, he pursued his research and obtained his PhD from Japan, University of Japan in 2018. He is a recipient of various fellowships, scholarships, and he has been working as postdoc in various places in Cambridge and Japan. And then where he was responsible for promotion of science. And then he is a recipient of Young Structural National Award conferred by Indian Association of Structural Engineers in 2023. At the moment, he is assistant professor at the Department of Civil Engineering School of Infrastructure, IIT Bhubaneswar, Odisha. Now, brief of the topic. As I said, the topic is advanced computer vision technique for structural health monitoring, where he has briefly described that in structural dynamics and vibration analysis, modal identification plays a vital role in understanding and characterizing the dynamic behavior of a complex system. He further said that operational model analysis is required to maintain large-scale and necessary civil infrastructure like roads, bridges, tunnels, etc. The present talk is non-contact video-based model analysis where we did not put any sensors for structures with arbitrary complexity using computer-based techniques. Then this non-contact method of operational model analysis using digital image correlation and tracking algorithm requires a speckle pattern based on the structure. And then this methodology is based on the is based on the machine learning technique, which is developed to extract the model parameters, and then the methodology uses complex pyramids and an unsupervised machine learning techniques. The above algorithm is first based on the numerical model and is implemented on laboratory scale model. Finally, the proposed methodology was used in the real recorded structural vibration video to determine the noise severity in the Tacoma Bridge and London millionaire footbridge. The model parameters extracted are compared with those from the available literature for vibration. Now, over to Professor Saravanan.
Yeah, thank you, sir.
Please continue.
Yeah, yes. Yeah, I hope my screen is visible.
Yes, sir. Yes.
Yeah, okay. Okay. Yeah. Thank you, sir. Thank you, Dr. Dhawan, for kind introduction. So thank you for the opportunity once again. So today, I would like to discuss on some of the advanced topic like which we are currently working at IIT Bhubaneswar. So we'll be discussing about something called as like computer vision techniques, so which can be utilized for structural health monitoring. So if I put into like if I like to like separate this topic into like two divisions, okay? So where structure health monitoring is one of the like most promising research area where like almost like for past 1 or 2 decades, even in Indian context, many works have been conducted. But here like we are introducing some advanced techniques, so where we are going to use something called as like non-contact based measurement. Okay, so generally structural health monitoring means we are going to use some sensors, so where you are going to mount the sensors onto the structure. Okay, so that is something like contact based, but today I would like to emphasize that there is something called as like non-contact based sensing technique, so where we could able to use the computer vision based methods to analyze the structures. So that's the basic maybe like abstract of this whole lecture that I'm going to discuss today. Yeah, so like first of all, like I would like to talk about the sensors and the sensing technology for the structural health monitoring. So as we all know that like sensors are something like an instrument, okay, that can detect the state of the system, and it is going to produce the appropriate information for the health assessment of the civil engineering structure. So we know that like it is something like an equipment which I'm going to like install onto the structure, and I'm going to record the response out of it. So typically it is used for like safety monitoring, active safety control, for condition assessment. If it is like a long-term condition monitoring of any infrastructure, let us say like a bridge, okay, and also to understand what is the current state. If there is some like loading that is going to come to my structure, so how my structure is going to respond to it. Okay, so and also to understand the deterioration, so how my structure is trying to get deteriorated due to the long term performance of it. Okay, so for the future performance prediction and the optimum maintenance strategy, because like we need to have a strategy, how am I going to maintain my structure. So I could not able to spend too much money for health monitoring of a structure, right? So I need to be having a optimal number of sensors, and also same time optimal placement of the sensors, and how am I going to do it. So this is something like the basic sensing technology which is required for structural health monitoring. So this slide is something like trying to help us to understand the state of the art. Monitoring is something like visual inspection. So there is no like method that is going to replace this particular visual inspection method, because that is something called as the most powerful and also the local non-destructive evaluation technique. So where I've just put these figures just to make sure that like not only civil engineering field but also for any aerospace, okay, or wind engineering, okay, or the underground structures. So visual inspection is very important. Okay, so as you can see, aerospace, the person is trying to check whether it is right or wrong. Similarly, this is something like bridges, so where you could able to see a big crane, and like they're trying to like there is a person, okay, so I hope you could able to see this. So where he's trying to understand, or he's trying to conduct some NDT testing, okay, to understand how the structure is or how the material is going to behave. Similarly, you could able to see there are like two engineers who are trying to climb the wind turbine tower, okay, just to understand the condition assessment of the wind turbine blades. And this is like underground structure where they're trying to understand the condition assessment of the underground structure. Okay, so this is something like I would like to like make you people to understand so how important the visual inspection is. Okay, so before we move into the next part of the things and like to understand the other advancement in sensing technologies, so please make sure that like there is no sensor in this world that can measure damage. Okay, so sensor is something that is going to measure the response of the system to some stimulus. So you have a system, you try to sense the response from that system when that system is subjected to some certain types of loads or some disturbance. Okay, so sensor is trying to just collect the response with respect to its own characteristic. If it is like acceleration sensor, it is going to collect the acceleration. If it is temperature sensor, it is going to collect the temperature data. If it is strain, similarly it is going to collect the strain data. So there is no sensor that can measure the damage. Okay, it is completely the data integration, okay, procedure, or the data processing or post processing techniques, okay, which is going to help us to understand, okay, how the structure is behaving. Okay, so where we need to have some effective health monitoring solution, okay, that need to be developed. Okay, so this is something like like there are like various types of loading. As you all like civil engineers, like I'm not going to go deep into this. There are like numerous structural loadings. Okay, there are like different types of loading as per the IS codal provisions. There are like which can lead to different damages. Okay, so which is like going to have different level of severity. Okay, so like right coming from the mild, severe, moderate. Okay, so then you have like extreme. So there are like different levels. Okay, so we need to like take a decision. So up to what level I'm going to allow my structure to take that load. Okay, or to have that damage, and how am I going to retrofit it. Okay, so the infrastructure rehabilitation, okay, is also like very important. So health monitoring is going to play a vital role in identifying and mitigating the potential structural damage, ensuring the safety and durability. That's the aim of monitoring a structure. Okay, so where like health monitoring, I could able to like completely relate. If there are someone who is new to this area, I can relate completely to the human body. So where we have a doctor, so where he is going to diagnose what is the problem with the human body, and he is going to prescribe some medicines to rectify it. Similarly, health monitoring expert is something like a doctor who is going to like take care of the structure, who is going to assess what is the damage in my structure, and trying to propose some methods or some retrofitting like methodologies or procedures that can be taken care, or like what else that can be done, okay, in order to take care of the structure. So where health monitoring is something like I just gave the example of the human body condition. In human body we have sensing systems, like we have 5 type of like sensing systems, which is like eyes, ears, taste, like touch. Okay, similarly, like when you come to a building and you are going to keep various sensors, so these sensors are something like sensing system. So where in human body there is a nervous system, okay, which is trying to connect all the information and it is going to give it to the brain, right? Similarly, here we have like a lot of like data collection point, and we try to collect those data and we try to give it to the sync node, which is going to like process those data. So which is something called as the data management system. Okay, so you can easily like have analogous with the human body. Okay, so coming back to this thing, so traditional method is something like contact sensor based methods. So where basically like we try to use some sensors to understand the vibration monitoring. Okay, so we always take care of the vibration aspect. Okay, so because that's the very easy and also like straightforward problem where you could able to get the response from the structure. Okay, so either you can use a displacement sensor or you can use accelerometers, but basically everyone use accelerometer because it is quite cheap comparing to the displacement sensors. Okay, so now, so this is something like a traditional method where you're going to have the contact sensor based methods. So now there are like a lot of issues. Okay, so maybe we can go into this sensor weight. Okay, so where there are like extra vibration of mass sensitivity. If it is a lightweight structure, there are some lot of wires which is going to disturb your response that you're going to collect, and where you're going to install your sensors. That is quite difficult, right? Because mounting the sensor, maintaining it, taking care of those sensors for long-term monitoring is quite difficult. Okay, so we need to have like neat like plan for the location of target where you're going to mount your sensor. So these are some of the drawbacks, okay, which is like practically like faced by the engineers. So how am I going to like overcome these issues, where we are going to propose some alternative methods? So there are like several non-contact methods. Okay, so as you know, okay, so where like laser Doppler vibrometer, which is something like a laser based method, which is quite expensive. Okay, it's like a high instrument cost and it requires like close proximity to the target structure. There are a lot of issues like where like the main problem is with the high instrument cost. Okay, it's quite expensive and you need a skilled labor, skilled engineer to do all those things. So now we are going to like propose something like where the same non-contact method can be used by a normal camera. Okay, so like a video measurement. So because nowadays I think like almost all the audience who are listening here, like everyone have a smartphone in your hand. Okay, and in that smartphone you have a camera which is like quite enough, which is having a quite good pixel resolutions, and also it is having a quite good frames per second, like FPS, and the sensing capabilities, where we could able to record the video of any structures that we are of interest. Okay, so here in this research, like or like in this like work, what we try to like propose is something like we are going to make use of some of the unsupervised learning algorithms, which is like coming under the category of machine learning techniques. So where we are going to use this unsupervised learning algorithm for the computer vision based methods, particularly for the operational mode analysis. So where here I put that as like blind model parameter identification, which is coming under the category of operational mode analysis, which is one of the powerful technique in structural dynamics. So where we are going to consider only the output from the structure. There is no input, there is no known input that is going to apply to the structure, because that is something like an ambient vibration we can take, or some traffic load. Okay, I'm not aware of what is the input to my structure, but my structure is prone to some excitation and my structure is going to vibrate, and I'm going to collect the response of the structure from the video measurements, and from there we are going to extract the displacement, and from there we are going to extract the modal parameters. That's the idea behind this work. So now, first method like I would like to propose or like introduce is something called as the video motion magnification method, okay, for the non-contact operation analysis. So this video like magnification technique is quite powerful technique, which was introduced by MIT professor in 2015 for the civil engineering structures. Okay, so from there, like from 2018 onwards, we are working on this method. Okay, so this is the methodology that we would like to propose. Okay, so I'm not going deep into the mathematics, but I would like to like take you all through the story behind this method. Okay, so I would like to classify into like three categories. Okay, the first one is the phase-based motion magnification method. So here, if you see the name phase-based, okay, so that means I'm going to handle this in frequency domain. Okay, so I have a video measurement, and I'm just going to like convert this video measurement into frames, number of frames, because combination of frames is something like a video, right? I'm just going to like decompose this video into number of frames. Okay, then I'm going to apply two-dimensional Fourier transform and filtering techniques. Okay, so where once I'm going to apply this Fourier transform, I'm going to get the amplitude and phase. So that's the reason like this method is something named under phase-based motion magnification. So once I get this amplitude and phase, I'm just going to play with the phase part, because amplitude is just going to give you the some disturbances, but phase is something, the phase matrix is something having the characteristics of the motion of that particular structure. Okay, so from there we are trying to do the multi-scale image decomposition. We are trying to use here the complex steerable pyramid, which is having a powerful like tool, so where we could able to decompose the image and extract the motion part. Okay, so once you do it, then you try to apply the magnification factor, which is something like alpha. It can range from 10 to 100, even like more than 100. So once you apply the magnification factor to each frame, so then you have a magnified frames. So then you come to the second part of the algorithm, where displacement extraction is very important. So which is like done using the Hotsu method. It was introduced by Professor Hotsu from Japan. So where we try to convert the frame into grayscale, because previously the frame, it is in color frame, right? We call that as an RGB, okay, red, green, blue. So we try to convert that into a grayscale, which is like very helpful for us to convert into a good binary image, where the matrix is going to have 0 or 1. Okay, wherever it is 0, that is like there is no structure involved. Wherever there is 1, there will be a white signal or like white part of the structure where structure is present. Okay, so once you do it, then you try to apply some thresholds and compute the centroid of each frame, and you try to extract the time history of that centroid. So finally, you have the operation mode analysis by the random decrement method. It is one of the powerful system identification technique. So where you try to convert the time history into the displacement physical coordinate, then you apply, you try to get the random decrement signature, then you try to extract the modal frequency and modal damping. So where we are going to just use the classical method, which is like logarithmic decrement method. So this is the like flow of the idea which we are going to discuss today. Okay. So before I go into the experimental like results or how it has been like conducted, I would like to introduce some of the sensors that we utilized. Okay, so this is something like a part of like wireless sensors, where you could able to see here. Okay, and this is the sync node, where you could able to connect to your laptop. Okay, and like it's something like wireless, you can just mount to the sensor. So this is something like we used for the reference based. So this is the camera that we have used. This was like we are trying to use some famous Sony NX cam, so which is like quite good camera, like video camera system. But nowadays, like we can replace this with some of the smartphones which we are having. Okay. So wireless sensors are used for the reference purpose, where it is helping us to calculate the measure the acceleration response. So then we have the video camera to record the video, where to have that vibration recorded. Okay, so then we could able to extract the responses and apply the computer vision technique. Okay, so that's the whole like process behind this work. Okay, so the aim is to extract the local pixel phase information. Okay, so where we could able to get the full field spatio-temporal motion. So this is the local phase-based vibration motion magnification method. So where you could able to see from a very simple expression, okay, I of x plus del x comma t, where so I is nothing but the image intensity. Okay, so where you have x and you have this del, which is going to give you the information of that motion with respect to spatio-temporal. X, which is spatial, and t is something temporal. Okay, so where this is the structural vibration part which I'm going to measure. Okay, so after this I'm going to implement the two-dimensional Fourier transform. So then I'm going to extract the multi-scale and localized filters applied. Then I'm just trying to replicate whatever we have discussed in that flowchart. Okay, you use displacement extraction method, where Hotsu method is used for fixing the thresholds. Then extraction of the model parameters is conducted using the random decrement method. Finally, you try to get the model frequency and the model damping, where you use the logarithmic decrement method. Okay, so this is the quick like flow of the work that we have done. Okay, so this is like small experiment that we have conducted. So where you could able to see there's a uniaxial shake table here. Okay, so where I have mounted a simple aluminum like 2 degree of freedom shear building, okay, kind of thing, where we have loaded each floors. Okay, and you can see there is a white box which is nothing but the wireless sensors, where I call that as node 2, 3 and 4. Okay, which where these wireless sensors are connected using the sync node, which I showed in the previous slide. So where I could able to access using my laptop. Now, in front of this figure, in front of the structure, okay, without touching the structure, okay, I'm just keeping a video cam and I'm just trying to record it. So we're just trying to give a free tap or like free vibration in unidirection, where my aluminum building is going to vibrate. Okay, so where acceleration response can be easily collected using the wireless sensors, which is going to give you a very neat result that is going to act as a response. But now the thing is that I'm going to use the video cam. So where I'm going to record what is happening. So then I'm just going to break down this video into number of frames and implement all the methodology which I proposed. Then I'm just going to compare whether I could able to get the response which is obtained from this wireless sensors. So that's the first point for the validation. So this is the acceleration data that has been collected or measured from the wireless sensors. So it is so beautiful, right? So it is having a free vibration. So where you could able to compare node 3 and node 4, which is because it's in the different floors, you could able to see the difference in the amplitude, and you're getting a very neat like frequency value. Okay, the first mode, which is at 1.855 hertz, and the second mode is something around 6 hertz. Okay, so this is so please try to remember this value 1.8 and 6. So let me try to like do the process, okay, using the proposed method, and we'll check that value. So now we have the temporal frames. So we are just trying to convert into grayscale and imaginary, like I mean the binary image. Then we are trying to extract the displacement, which is so much random. So then I'm implementing the system identification technique. So where I could able to get the random decrement signature. So from there, I'm going to extract the parameters. So here, I'm just going to get the first mode as 1.855 and the second mode as around 6.09. So which is like quite close, okay, with the values whatever we are extracting. But one point that we have to like mention here is that, so to do this part, so wherever that filtering I mentioned in the slide, so I need to fix the range of that bandpass filter. Okay, so I should know that my structure is having some value between 1 hertz and 2 hertz. So then I could able to happily like extract this value. Okay, that is one sort of like a drawback we could able to call in 2020s, like we try to do this. Then in recent years in 2024 we try to like improve the technique without fixing the bandpass filter, how we could able to extract. That's what we will be seeing in the future slides. Okay, so now this is the next simple experiment where you have a cantilever beam. Similarly, you have a video camera. So here, like I didn't mount any sensors onto the cantilever beam because it's like a very light structures. So where that extra mass might influence my results. So we use the laser Doppler vibrometer, which is one of the powerful equipment, which will give a very neat and the like accurate results. Okay, for like measurements. So we use this equipment and we have done the we have obtained the results. So this is the displacement response from the LDV. So which is like really good, and like we could able to extract as like 2.832. So similarly, we tried to used for the video based measure. So where you could able to see here, so the video whatever we captured is having some of the, when you try to break down that video and magnify and do all those things, there are some of the noise components which we could able to see, okay, from the face part of the matrix, okay. So where we could able to see some of the disturbances, okay. So where we extracted the displacement from the video, okay, and we could able to apply, and we got more or less like quite good results, like 2.8 hertz, okay. So this like gave us some confidence that we could able to implement this technique on field. So this is something like we just like randomly like implemented this method. So where I'm just trying to run this video, okay. So this is the original video which has been captured, okay, from the random bridge where you have a light pole, okay. So now like why I'm showing light pole, because like the Kajima Corporation, so it's one of the famous steel company, so where they want to understand the frequency of the secondary element which is there in the bridges, okay. So this is the normal video, so where you could not able to see any of the vibration that is happening, but I'm just going to show this video, so where you could able to see the magnified one. So see, basically this bridge is prone to some ambient vibration, okay, and there might be some vehicles that is passing on, where this light pole will be vibrating, but it is not seen in our eyes, okay. There are like so subtle small motions which could not be captured by the naked eyes. So now what we did using this method, you could able to see how this, you just see here how the light pole head is trying to vibrate. So basically this vibration is happening, but which we could not able to see, but this method, phase based motion magnification method, is trying to help us to understand how this structure is actually vibrating, okay. So this is some of the proof where you could able to appreciate, where we could able to extract the small vibration which we could not able to see. So now like I hope you are all sitting in a room, so let us assume that like you switch off the fan and you just observe the fan. So when it comes to a still, so you can, I mean, I can assure you that like you could not able to see any of the vibration in that fan. But if you just record a video and apply this method, you could able to see that blades are trying to vibrate. Okay, so that's what we are trying to show here. So we tried to conduct the experiment in Shin Nakagawa Bridge in Japan. So this is one of the famous bridge. So where you could able to see the pictures of this bridge. So where I conducted the experiment and recorded the video. Let me show the results. Okay, so which will be more interesting. So this is the girder lateral mode, okay. So original response. So because of the ambient condition, vibration is something like invisible. You could not able to see any vibration in this video, okay. So where actually the video is running. Let me just run this video where we have applied the magnification factor of 100 hertz in the range of filtering of like 0.3 to 0.5 hertz. Okay, let me just run both the videos. Okay, so you could able to see you could able to see the vibration. Okay, so this is the girder lateral motion. So I hope like now you could able to feel the vibration, right? Okay, so this is the vibration that is happening because of the ambient condition. Okay. Yeah, so these are all the results that has been extracted. Okay, so for the first like mode, okay, the lateral mode, okay, of the girder, using the software, it was like 0.44 hertz. By using the motion magnification method, okay, so coming to the frequency value, it is like 0.46 hertz. Quite reasonably well, right? So it is, if we could able to capture. So just by recording the video without installing any sensors, I could able to get the first lateral mode. Okay, similarly, like we have results for vertical mode as well. So just observe here, you could able to see like there is no vibration that can be seen here. Okay, so because this is the original response. Okay? The original, say you could able to see there a car passed here, right? So a couple of cars are passing. Let me just play it again. I hope you can see number one, number two. Okay, I hope you can see some cars are passing, but still you could not able to see any vibration here. But technically this bridge is prone to this traffic load, right? So let me just play this video. So where you could able to see how this bridge is trying to have this motion. Okay, so where when that car is going to pass, you will have that more vibration. Okay, because that load is, you could able to feel that, right? Okay, so this is the vertical vibration. Okay, so from keeping the sky as the reference behind, you could able to see how my structure is trying to vibrate. Okay, so where you could able to extract the vertical mode. Okay, so this is the method that we use. So we try to convert into grayscale and binary image, and like we try to get the so-called as like vertical mode. The first girder vertical mode using the Dyna software was 0.36 hertz. From the motion magnification method, both in X and Y direction, we could able to extract around like 0.35 hertz. Okay, so the Y direction was the vertical, where you could able to see from the figure, and it is like exactly same 0.3516, and it is like 0.36. So where we could able to like achieve the quite good results. So then we try to implement the method in the Yokohama. Like there is a bridge, okay, so where you would able to see there is a crossover bridge. Okay, so we have some of the results. So this is the model that we have done using this abacus. So where you have different values, like this is like very simple like analysis where you would able to get the values 2.1557, all those things. So now let me just show the power of this method. So where this is the original response, so where you could able to, I mean, it's like vibration is invisible, right? You're not able to see. That's the reason I have kept these yellow dotted lines, okay, just to keep that as a reference to show how it is vibrating. So now we're not able to see anything. The same video, let me just play this. So now you see, you could able to appreciate the motion, okay? So because of some of the ambient vibration, we could able to see the vibration, okay? So when the video is amplified 100 times. So this is for the lateral motion, original response. Okay. So where like it's like completely invisible. This is something like bottom of the bridge. Okay. So where you could able to see some of the shadows. That means some vehicles are passing through. Okay. So let me just play this video. So where you could able to see the lateral motion. Okay. So you could able to see the motions. Okay. So from here, it is quite good for us to extract the data. Okay. So this is for the lateral motion, so where you could able to extract the responses. Okay, so some of the practical cases I would like to show. That's the reason I'm showing quite good number of videos, so that like at least you will understand what we're trying to do here. Yeah, so I'm just trying to show a couple of results, okay, which we have obtained. So where you could able to see some of the displacement results that has been extracted, and we are getting like 2.344. Okay, so it's like quite a reasonable value as compared to the abacus model. Okay. So then like we try to implement the method in different parts. So where like we could able to like implement for any structural members, not only bridges, like for secondary elements like light poles or like any part of the structures, we could able to do this exercise. So this is the King Kocha junction. So where, which is like quite famous area, okay, at Yokohama prefecture. So where you have different light poles. This is like a double-decker bridge. Okay, it's an expressway. Okay, so where it has like different types of light poles with signboard, without signboard. So why I am saying this, because without signboard, the mass of the light pole is quite low when comparing to with signboard. So that is going to change the dynamics of the light pole results. Okay, so we have different classifications. Okay, so this is the like, so now I'm not going into the bridges or like installing any sensors or stopping the traffic, which we usually do it, right? But now what we're doing, I'm just like calmly standing in the pedestrian, just recording the video of this particular structure. And just for the reference purpose, I'm also keeping the LDV laser Doppler vibrometer, just to prove that the results that we're obtaining is good or bad. Okay, just to have a validation. So we're just, without doing anything, we're just trying to record the responses. I mean, record the video, which is nothing but the response. Okay, the video is the response and the camera is my sensor. Okay, so now let me just show the different types. So these are all the like case studies. Okay, so I have just selected 4 different types of light poles. So where these 2 light poles are at, I mean, all 4 are at different locations, and these 2 light poles do not have any signboard, but these 2 light poles have a signboard. So this signboard looks small, but it really weighs like around like 15 to 20 kgs. Okay, so that is going to change the like characteristic of the light pole. Okay, so this is the results that has been obtained from the laser Doppler vibrometer. Okay, so it was just like quite decent results. So where we could able to get the response of like around 1.56 and 1.6. So almost like above 1.5 and below 1.6. Like it's quite good amount, I mean, good range that we got. And that has been like cross-checked with the various literatures and also like with other experiments. So the value is like quite good. So now keeping this in our mind, so we try to like implement the video motion magnification. Okay, so this is for LDV. So now I'm just trying to like separate in like the frames into different like I'm just trying to show the frames. Okay, so in the interval of 10, just to like make sure that how that light pole is trying to vibrate. So I'm just trying to just impose over the grid map. So where you could able to see, just concentrate on the light pole head. Okay, so where it is like trying to dislocate from, it is trying to have some different locations in every 10 frames. That means it is vibrating. Okay, so it is trying to change its position after we magnify the video. So that means it is trying to vibrate. So where we are going to extract this vibration part, that's what we're going to do. So this is the extraction that we have done. Okay, so though it is like a random vibration, so we have created the like free decay random decrement signature. So from here we are trying to get the frequency values, which is like 1.52 and 1.6, which is like quite reasonably well good data that we have obtained. Similarly, this for the different poles, that is P3 and P4. So where you could able to get like sometimes like you get a very good results. So you could able to see how the light pole head is trying to displace. It is having a very neat displacement. Okay, so where the frequency is something like more or less same 1.61, 1.64. So this is how like we try to downsample the data. So the whole video I'm not going to use because computational it is quite huge and like it takes a lot of time. So what we do was like we try to do the downsampling of the temporal frame, okay, which is of our interest, which saves a lot of time. Okay, so then you try to concentrate, try to convert into grayscale just to avoid all the disturbance, and binary image, so where you could able to see my structure. So this is my like extraction, okay, motion extraction. Okay, and this is the comparative results. So I mean the results, I'm just trying to put together all the results here. So where you could able to have a good comparison, like 1.56, 1.52, 1.61, 1.64. Sometimes it is having a good match. Okay, so reasonably the vision based method, computer vision techniques is quite well. Okay, both for the bridge structure and also for the secondary element. Okay, but as I mentioned earlier, so one drawback is, if I could able to have this value in hand, okay, with some LDV or some other sensor, then I know in what range my structure is going to vibrate. Then I could able to fix that value, okay, as a band pass filter in this technique, and I'm going to extract it. But suppose like, see in this research work, like of course we have the reference values, but in practical, you just directly go to a site, you try to record a video, then you try to implement this method, but we don't know what will be the frequency range. Let us assume it might be 1, it might be 1.8, it might be 2.2. Okay, so we don't know this value. So now, so there is a question, how am I going to fix my band pass? So that is a big drawback that we had. Okay, so then recently we're trying to work over this drawback. So where, how to overcome this without fixing the band pass? How am I going to extract the frequency value? That's a very big question that we had, and we have done that part. Okay, so that's where the whole method is going to like come. Okay, so where I call this method as like unsupervised learning algorithm, where machine learning, artificial intelligence or machine learning technique will be utilized here. So where it is going to extract the like model parameters blindly from the videos. Okay, so that's the power of this method. Okay, without fixing any bandpass filtering and without doing all these computational efforts we had, this method is completely like overruling it, and it is like quite very efficient and like time consuming. Because for the previous method, it takes like almost like 2 hours, 3 hours. It depends upon the video content. If it is like 15-20 minutes of video, then it really takes time. But the current method which I'm going to discuss, it's quite fast, and like we could able to extract this. So I'm just trying to like reappropriate the method. I'm going to propose a new method. So where I have an input video, I have an image filtering, and I'm going to do the multi-scale decomposition and have the face extraction. So up to here, more or less, I'm going to do the same thing. But then after, I'm just going to get into the unsupervised learning algorithm, where I'm going to use the very basic and powerful principal component analysis method on the motion matrix. Once I do this, I could able to extract the principal components. So because this principal component is nothing but it is going to give you the major mode or the major mode participation that is going to take place. Okay, that information is there. Once I could able to have this, then I can apply any modal decomposition technique. So here we have applied analytical mode decomposition. We can go with dynamic mode decomposition or any system identification method, we can use it. So here we are applying analytical mode decomposition and extracting the principal components. Once you extract the principal components, then we are just trying to implement the random decrement technique, extract the free decay signal, then modal frequency and damping ratio. So now, so this 3 boxes, which I'm going to like do is something like very powerful method. Okay, so over the previous technique that we discussed. Okay, so here in principal component, like principal components are calculated using like 2 methods, which is like singular value decomposition and the eigenvalue decomposition, so which we will try to discuss. So I think like this is the the time history response. Once you collect, you have the temporal displaced intensity. I hope like you understand this part. So what you do, then you try to do the multiple band decomposition technique. You have the complex stirable pyramid to extract the phase. So then you try to, so this stirable pyramid is something like again, it was introduced by Professor Freeman like in 1995. It's like quite old, but very, very powerful. Okay. So where you could able to decompose into like high frequency and low frequency part, and you could able to extract it. Okay. So then once you do it, then you have the band pass oriented filter. Then finally you try to like have the octave bands. And once you have this octave, but in this research we used half octave, that means 8 bands. Okay. Which is used for the better results. Okay. So where we have the quadrature filters. Okay, so that has been utilized. The convoluting process is done with the frequency domain by component wise multiplying functions and performing the backward discrete Fourier transform to get the image. So we're just trying to have the first you try to decompose, then you try to reconstruct. Okay, that's what you try to do. Yeah, so this is the complex stirable pyramid. Okay, so once you try to have this filtering part, then you try to decompose it, you try to understand what is there. Okay, and you try to reconstruct that part. Okay, so once you do it, okay, so you try to decompose this I of x plus dx x comma t into like a q of omega. So which is again going to have, this is something like filter response. Don't go with the equations. So we'll just go with the understanding of what just the physical understanding. So we have the filter response. Okay, so once you have this filter response, it is going to have the combination of the local amplitude and the local phase. Okay, so this is the amplitude first plus phase. Okay, so now I'm just going to play with the phase part. So where this phase part is extracted, which is going to represent it like this. So once you get the phase part, you try to remove few of the temporal mean and you're going to get the decomposed part. Okay, so that's what we're going to play with. Okay, so now I have the phase part. I'm trying to like decompose the temporal mean. Then it is something dying down to the very classical structural dynamics. So where you have like trying to expose using the modal superposition as a linear combination of the modal responses. So where we always have the mode shape matrix and the modal response vector. Okay, phi of x and q of t, which is nothing but this is something like quite commonly seen in any structural dynamics book. Okay, you take A.K. Chopra or Clough and Pensive, you can see this equation, which is like we are just trying to correlate with respect to the classical structural dynamics. So once you try to decompose it, you're just going to get the ith mode shape and the ith modal coordinate, nothing else. So, but this method was proposed in 2017 by Professor Young at Michigan University. But they have noted down, this line was taken from his paper. Due to the over completeness with high spatial and the low modal dimensions over the complete model, the modal identification problem cannot be solved directly. So this is the conclusion they have made in this paper. But we tried to overcome this part and we have solved this issue, whatever they have claimed. Okay, so that's the reason we are using the unsupervised principal component analysis. So where the crux of this PCA technique is to minimize the dimension. Okay, so where there is a huge data set that is coming out from the motion matrix. So now I should be carefully extracting the phase, so where that the most of the so-called as that principal component is present, that I need to extract. Okay, that's the procedure that we are going to have. So I'm not going deep into the math, but this one like will quickly go. Let us just assume that there is a large data set. Okay, so now what is happening here? So you have the row wise mean value, that is x bar. You try to subtract it from the x. Okay, so then you get this expression. Then you try to get the mean subtracted data, that is m, that is capital X minus x bar. Okay, then you try to get the covariance matrix. So this covariance matrix is very important step in this method. Okay, so once you get the covariance matrix, so you can try to get the components by just getting the maximum variance value. Whichever is going to have the maximum variance, that is going to become the first principal component, and followed by the second maximum variance value will become the second principal component, and so on. Okay. So the power of this method, so called as this eigenvalue decomposition, is going to tell you how many modes are present in your response. Suppose you try to take a video and you try to analyze it, and you should know that, okay, from this response, at the max, I could able to extract, let us say 3 modes or 4 modes or 5 modes. That information, that index, you're going to get from this eigenvalue decomposition, which is like quite classical and powerful method. Okay. So once you do it, then you try to implement the single value decomposition just to get the motion matrix, and you try to extract. That's what you try to do. So I'm not going into deep into the math here, but just try to understand the flow behind this. Okay. So once you get the like covariance of matrices, okay, so then you try to get the principal active components. Okay, then so PCA can be significant. So now PCA has significantly reduced the dimension of motion matrix. So where it is going to have very small number of components, which is going to linearly you can fit it and get the principal component. Okay, so the governing principal components. So this is going to give you the information on the dominant frequency modes. So once you so now you get the modes, but the problem is now these are all like mixed modes. So now you need to have some more decomposition method to just to decompose it. Okay, so that's what we are going to use, the analytical mode decomposition. So this method is something like taking help of the Hilbert transform. Okay, so which is also like powerful method. Someone, if you're interested, at least some researchers, if you're interested in math, you can go and read into these things. So since we teach to many students, like we always go, like we love to discuss about math. So like now in AMD method, like what we do is like we try to have the so it's like quite simple. Suppose you have a signal and it has a lot of frequencies, and how you're going to decompose the signals. That's the whole crux of this method. You have like a signal, suppose it has like phi or n significant frequency component, and how am I going to decompose? That's the power of this. And more powerful technique than AMD is dynamic mode decomposition, so which we are currently working on. So then we have the random decrement method. So this method I think we discussed, right? So where we are trying to get the random free decay signal. From there we are going to implement the logarithmic decrement and the model damping ratio. This I hope like these formulas are very classical formulas, which is like there in any classical books. Okay, so you're just trying to get the free decay signal just to get the damping part. Okay, so now I'm just trying to show the proposed model. Okay, how it is going to work for the numerical simulation. Okay, so where you have the 12 degree of freedom model. Okay, so it is all like simulation that has been done in MATLAB. Okay, so where you have the 12 degree of freedom system and you have the initial velocity, and you try to like collect the responses from all 12 channels, because you have the feasibility to get the displacement, or if you want velocity or acceleration, you could able to do it, and without noise, of course, for the simulation purpose. And also we have done with noise. Okay, so these are some of the mass, stiffness, and the damping matrix that has been taken. Okay, so now we are trying to fix it to the 4 theoretical modes. Okay, just for our understanding. So since we have fixed it, so we could able to prove that eigenvalue decomposition is trying to give you 4 number of indices. Okay, so from this plot you could able to get how many like dominating modes are present. Okay, that's the crux of EVD. But there are like 4 components. So these are the 4 components that has been extracted. So this is like quite straightforward problem. It's a numerical simulation. You have like mixed modes. You can see there are like number of frequencies. I think from the principal component 1 and 2, you could able to see there are like almost 1, 2, 3, or 4. Even there is 4 frequencies that is present. Okay, so now how you're going to extract these frequencies? That's the reason we are going to use the AMD method. So where I'm just trying to get the first modal frequency as 5.3 hertz. Similarly, second modal frequency is 10.10 hertz. I could able to easily classify all 4 frequency values. Okay, 13.9 and 17.7. Okay, so that's the power of this method. So now I'm going to introduce the noise. So because this is a practical case, right? We need to have some noise in your response that you collect. So then you try to understand how this signal to noise ratio is affecting my method. So we have varied from 40, 50, and 60, and only the amplitude or the power spectral density is changing. Only the energy of the signal is changing, but the frequency value is not changing. So that means this method is quite powerful. So this is the table. So where you just see the error percentage. It's like less than 1%. That means it's like quite good. Okay, both for the noise and without a noise conditions. Okay, so this is like quite good method. So where we could able to implement for the practical cases. So what we did was like we tried to implement on some of the vibration data that is available, okay, which is like called as the benchmark vibration test. So this is the simple single degree of freedom system and multi-degree of freedom system like experiment that is conducted by Professor Kyon in Missouri University of Science and Technology in Rolla. So this is something like a normal video which is available. I think it's an open source video. So the quality of video is just 480 pixels, which is like quite low quality. So you could able to see the test that has been conducted. Okay, so it's like a very normal single degree of freedom system. There are like 3 different systems and the vibration is like applied. Okay, so I hope you all understand what is a resonance effect. So whenever the input excitation frequency value is trying to match with the structure's frequency, the resonance happens. That means the structure is going to vibrate drastically. Okay, that is something called as resonance. So in this experiment, he is trying to show the same thing. If you have like different heights of, so why different heights? Because different frequencies. Okay, so the tallest building is going to be affected by low frequency. Okay, so now you could able to see this is something like a sweep time sign test where the frequency value is going to change from 0 to let us say 20 hertz. It is going to keep on change from 0, 1, 2, 3, 4. So now you could able to appreciate wherever the structure is trying to go close to the input excitation and the structure's excitation, you could able to see that the tall structure is trying to vibrate fast. Okay, so that means the frequency value is approaching to its structure's frequency. Okay, so exactly at the point it is going to match, you're going to get the resonance. I think you could able to see. So this is the 4 hertz. You could able to see at 4 hertz there is a resonance. Okay, so you could able to see the resonance. Okay, so this is like quite very simple experiment that has been conducted. So now why am I showing this video? Because now we know that this particular tall structure is excited at 4 hertz. So now my method, my proposed method should give that 4 hertz because this structure is trying to have the dominant frequency of 4 hertz, right? So my proposed method should give that, yes, this particular structure is having 4 hertz. If I'm going to prove it, then the proposed method is fine. So that's what we're going to do. Okay, so just remember this particular structure is exciting at 4 hertz. So let me just, so this is the video for multi-degree freedom system. So okay, so again, like we have the values. I'm just going to show those values. Yeah, so now this is the blind identification. Okay, so now once you have the frame, let us assume that you have a frame of a structure. And when you do the 2-dimensional Fourier transform, so I think we discussed about this amplitude and phase part, right? So this is how it is going to look like. So from amplitude, you could not able to sense how the structure is vibrating. It's quite difficult, right? You're just seeing this small white lines, which is like not giving me any information. But you just see the phase part, you could able to clearly see like, I mean, there is some like some disturbance that is happening. That means this is the motion matrix, which is going to give you a lot of information about the same. Okay. So this is the implementation algorithm. Okay, so I'm just quickly going through it. You have the frame decomposition, you have the amplitude and the phase part. Then you just trying to play with the phase extraction part. You try to remove the temporal mean. You go into the motion matrix construction. Okay, then PCA technique is implemented to get the principal components. Then mode separation is taking place. Then finally, you try to get the free decay signal and model frequency and damping ratio is calculated. Okay, that's what you're going to do. So by doing this for single degree freedom system, we could able to get like very neatly like 1 value, and for multi-degree freedom system, we could able to get 3 values. So I'm just going to show the results. So this is the results that has been obtained, okay, from the video measurement. Okay, so where you could able to see that the frequency value that we measured from the video like computer vision technique is something like 4.06 hertz, which is like having a quite good match with 4 hertz, whatever we have seen now. Okay, so the video is having 30 frames per second. Okay, so just someone, if you're interested in the dynamics behind this, so we know that like every sensor has its sampling frequency. So the sampling frequency is why it is quite important. Why? Because as per the Nyquist rule, the half of the sampling frequency value is something the max that you would be able to measure using that particular sensor. Okay, so for example, if your sampling frequency is 50 hertz, okay, so then as per the Nyquist rule, up to 25 hertz, you could able to clearly get the response. So now we have 30 FPS is my camera's frames per second rate. So now this 30 FPS is nothing but I could able to correlate this FPS with respect to the sampling frequency of my sensor. So 30 hertz. As per the Nyquist rule, I could able to capture the vibration up to 15 hertz. Okay. So now since it is 4.6 hertz, I'm happily capturing. Suppose if the structure's frequency is more than this, then I have to increase my FPS. Okay. So please try to note down that. So here we have used very, I think some might be interested to know the what is specification spec of the computer device. Like we use like normal high performance computing Intel i7. Okay, so where we have like 16 GB RAM. Okay, it's like quite normal like laptop that we have used. Of course, you can use any type of high performance computing workstations to do this. So these are all the results that we obtained for the multi-degree freedom system. So where the values are something like 4.35 and ours is 4.41. So it's like quite comparable. Okay. So the error is less than 2%. Okay. So it's quite good results we have obtained. So next, I would like to implement on some of the classical videos. Okay. So where this can be like this method can be proved. Okay. So this video, what I'm showing is something the London Millennium Bridge. Okay, which is located in London. Okay. So it is quite famously called as Wibbly Wobbly Bridge. Okay. Why? Because in 2000, this is a pedestrian bridge. Okay. So in 2000, this was open to the traffic. I mean, open to the public. But immediately this was closed due to the vibration that is happening. So then there was an expert committee to have some of the vibration control devices. Then it was again opened. Okay. So this is trying to exhibit. Even now you could able to see from this video that there are a lot of tourists who try to walk in this bridge. Okay. So they could able to feel the vibration. Okay. So I have personally like had an experience of this vibration. Okay. In 2016. So this was like some of the, so this bridge is having a characteristic something called as the lateral excitation. Okay. So there are like a couple of famous research articles that has been published. Okay. So once this this bridge was opened and it was closed due to some of the vibration effect. Okay. So now, so we'll try to understand this part. So we have like a random video, which is like captured by some tourist, which is again open source. So we don't know what is the excitation frequency that is vibrating. So we're just trying to get the video from there, and which is like quite low resolution, 480 pixels. Nowadays, it's something like so-called as like poor quality, right? So I'm trying to downsample it, and I'm just trying to get some part of the bridge where I could able to extract the responses. So after extracting it, okay, I could able to get the response, which is nothing but the bridge swaying, okay, which is occurring as per the pedestrian's walking frequency. There is a synchronization between the pedestrian walking frequency and the bridge swaying. Okay, so that's what we are trying to do. So there are like 3 dominant frequency modes that we could able to extract. Okay, so we could able to compare these values, okay, with respect to the experiment that has been conducted way long back in 2002, okay, by Professor Pavic in Italy. Okay, so he tried to like get the data. We could able to get the error less than 1%. So that means the proposed method is so powerful that we could able to implement to any practical situations. Okay, so this is the next case study I would like to discuss is the Tokomo Narrow Bridge. Okay, so I hope you all know this bridge. Okay, so this bridge got collapsed. Okay, so due to the wind load effect, right? So aerodynamic condition, so which was not designed for wind load. Okay, so where you could able to see that the main span of the bridge deck, okay, it is just like trying to have a huge vibration. Okay, where you could able to see this is the recorded video long time back. Okay, so the bridge oscillated due to the aerodynamic condition. It got collapsed due to the torsional effect. Okay, in 1940 this got collapsed. So this is the open source video again. So we try to take this video and try to extract. Okay, so how we could able to get the frequency values. Okay, so this is the bridge deck part. Okay, so which we considered for our analysis, because like we did not consider the torsional mode, because in the previous slide if you see, so this bridge deck is quite reasonably vibrating well for our method. This is like too much vibration and it is having a twisting part which is having too much non-linearity. Okay, so we try to consider this part. Okay, so where you could able to see the vibration that is like visible, right? So we try to extract this video and decompose it, get the amplitude and phase, and get the responses. So coming to the values, okay, so if you could able to see the value, the values are quite reasonably matched with respect to the like reference values. Okay, so the summary is that like the output that we try to like get from the video is more than enough to get the like model parameters by using the proposed like blind like source like separation methods, like where you have the unsupervised PC and AMD. So currently we're trying to also like we worked on like replacing PCA with like non-negative matrix factorization methods. Okay, there are like a lot of improvements that we can do with these methods. Okay, so the PCA is so powerful that it could able to reduce the motion matrix dimension. It is also helping us to extract the principal components. Okay, so it's quite powerful method. And again, like decomposition for the model decomposition methods like AMD was utilized. We can again use some powerful methods like DMD techniques. Okay, so the conclusion is something like where you have that simple digital camera based video measurement, any smartphone. Okay, we can use to estimate the model parameters of the real time structural vibration. Okay, so where this type of like simple measurement, okay, so video that we collect, it can be used for the real time infrastructure performance, like operational maintenance, like resilience assessment. Okay, so nowadays, like we also had a thought that like we have a surveillance camera like that has been fixed in most of the places. We have like traffic cameras. Okay, so where like if you could able to have some like video of that. Okay, so of some buildings or some infrastructures, if you could able to collect those videos and send through the cloud, we could able to monitor that particular structure by assessing the frequency or the modal values, which is going to give you a quite good like information, because the model the frequency value is going to give you a better understanding of your structure. Okay, so how it is going to vary, how that value is changing with respect to last year and this year because of various factors, right? So all those things, it will be like really helpful. Okay, so that's the conclusion I would like to make. So these are some of the references and some of the publications that we have published. Okay, so if someone is interested, so you can refer to it. You can also like feel free to contact. I would able to share these papers. And also, I would like to inform all the participants that at IIT Bhubaneswar, we are conducting the 1 week short-term course on vision-based condition assessment of civil infrastructure under the sponsored from the Ministry of Education, Government of India, under the program called as this GYAN course, Global Initiative of Academic Networks. So we would like to like invite you all to participate in this. The course faculty will be like we are inviting the professor from University of Houston, Texas, Professor Vedas Hoskare, who is also like an expert in this computer vision technique. So where he has proven his works at University of Illinois Urbana-Champaign. So now he is at University of Houston. So he'll be coming and he'll be staying in IIT Bhubaneswar for 1 week. Okay, so where we'll be having like a detailed coursework with a lot of practical things. So some of the interested participants can please register for this, and you can come to IIT Bhubaneswar, or like at least like remotely you would able to understand more about this method if you are interested in this. Yeah, thank you for your kind attention. If there are any questions, please ask me. I'll be very happy to
Yes.
answer.
I mean, Professor, can I ask one or two things
Yes, sir.
before I give to the audience?
Yeah, sure.
Hello?
Yes, sir.
See, you use the term PCA plus AMD plus RDT.
Yes.
I mean, combined together will give better result.
Yeah.
What we are interested to know the frequency, natural frequency.
Yes.
Of first mode, second mode, or third mode.
Yeah.
So combining all this PCA, AMD, and RDT, you mean that this will be the when we have to add all these three and get the frequency, or can we do separately?
No, of course, like we are doing it separately, but each method is supporting each other. That's what like we have a hybrid techniques here, because like see actually what we are planning to do is like we are trying to develop an app so that you could be able to install, take a video in your mobile and I mean give input of that video into that app, and that is going to give you the value. So no need to worry about the methodology here, because that is going to be kept at the back end. Okay, so that is going to do the whole process of it. Okay, so why we are having this AMD method? Just to decompose the modes, and of course RDT is to get the model frequencies in a very neat manner. That because getting the model frequency from the free decay signal is like more powerful from the random signature. That's the reason we have used that. It's a powerful system identification technique.
I see. The second thing is how to work out the signature of healthy healthy signature of a bridge, say, we are dealing with vibration.
Yeah.
I mean,
So
how to detect this healthy signature, and seeing the safety and durability part. I mean,
yeah.
which frequency or which signature would give us the that this structure is safe and durable?
No, for example, once you have a constructed structure, at least like for 10 years, we are not worried about the structure. Maybe at least 15, 20 years, we are not worried. After that, the problem starts. So if you could able to have the video of, like, let us say, like we have a structure of 5 years old, okay,
Mm,
and you try to record that video and you try to get the frequency value, and you try
mm,
to continuously record every year or like every 6 months in that period, okay. So
mm,
then you try to compare the frequency values, whether the frequency value changes. Of course it will change, but if there is a drastic change, and also you could able to for example, if you have a bridge, like there is a bridge pier, there is a girder, you can compare different structural components, and you could able to extract the frequencies, and you could able to compare again with the same values, keeping that as a reference with the next year's value or next interval value. Try to understand whether the structure is safe or not safe, because while designing and while after construction, we know that this will be the range for the frequency of this particular structure. If there is a variation or out of that range, then obviously your structure is prone to some deterioration. So then you should, this is something like global monitoring. So
mm,
then you have to
mm.
go to the next step, which is called as the local monitoring, where you have to understand whether it is like problem with my bearing part or girder or like joining, or is that my pier is settling down. There are like various factors when it comes to the critical conditions.
Then finally, you talked about the failure of Tacoma and Millennium Bridge, London.
Yes.
I mean, I feel that this is bridges were a failure due to the, I mean, omega and coincide.
Yes.
Was that was the I mean cause of failure?
Yes, you're right. So for example, if you take Tacoma Bridge, so
Mm,
this got failed in 1940. So that was
mm,
not designed for wind load. So when there was an extreme wind, okay, so that load, that frequency of that input excitation, when it got matched with the bridge excitation, okay, so that was the
mm,
torsional mode, okay. When it got matched, the resonance happened, where you could able to see there are a lot of twisting. So then, which was not basically designed for it, and it got failed. So that was a big lesson for the structural engineers. Later onwards,
the-
they try to consider for the wind load. Similarly, if you take the London Millennium Bridge, they never consider the pedestrian load, because I think like there are like a lot of students used to do some experiments using minions. So when you try to like excite the minions at different rates, at some point of time, all minions will get synchronized. That's the human behavior also. Suppose if there are like 100 people are walking randomly in a bridge, after a certain time period, those 100 people will be synchronized to some certain motion or certain pattern. So that synchronization will have one frequency. If that frequency is going to match your bridge frequency, that is going to have a vibration. That's what happened with the London Millennium Bridge. That's the reason
mhm.
they installed almost 6 to 7 vibration control devices, okay, at below the girder, just to arrest those vibration. And they allowed few vibration where that has become so famous among the public. That is like a famous tourist spot where you walk in that, and you experience that vibration while walking. So where still you have that sway, lateral sway is allowed. Yeah. So these are like two important case studies.
Uh-huh.
Yeah.
Thank you. Because the other questions, please, I mean, one by one.
Yeah, so
Please.
there are a few questions in the Q&A. The first question is asked by Mr. Mohammad Aslam. The method is similar to digital image correlation, but without surface preparation, correct? One limitation is that the camera must remain fixed. Would wind-induced movement affect the accuracy of the results?
So can you go one by one? Like what is the first question? So who asked? Like,
For,
can I see that?
yes, the question are in the Q&A box on your
Achha, okay.
screen. Yeah,
Okay.
you just open it.
Where I should access this?
You have to just click on the Q&A.
Achha, okay. Q&A. Yes.
Yeah.
Yes, I could able to see. So the method is similar to digital image correlation, but without surface preparation, correct? See, digital image correlation is something having a different methodology itself. Of course, for digital image correlation, as you said, surface need to be prepared. You should have a speckle pattern or some reflectors, and you try to like uh, take the frames and you try to understand how that particular pixel is changing or like how that tracking is taking place. But here, of course, there is no preparation required. Um, the methodology itself is completely different where we are having a different image processing technique. Okay, so both come under image processing, but this is completely different. So where we are not going to deal with each pixel, but we are going to decompose the frame into two-dimensional free like Fourier transform and decompose into amplitude and phase part. So where phase is going to be the motion matrix, where I'm going to play with that matrix. Okay, that's the answer for your first part. One limitation is that camera must remain fixed. Would wind-induced movement affect the accuracy of the results? Yes, of course it will be affecting. So I think nowadays there are like a lot of, for example, in cameras, there is something called as anti-shock absorber. Okay. So where you can switch on that and you can place it on tripod, and that is not going to give a big problem for your video that you're going to measure. And also this method is so powerful that minimum 10 seconds video, that if you have a good video of 10 seconds, this method is quite powerful to extract. For example, the Tacoma bridge, we had only 7 seconds. Still, we could able to extract the value. So minimum is 10 seconds. Maximum, of course, you can go with a minute or 2 minutes, 3 minutes, 5 minutes, 30 minutes. It depends upon the computational capacity that you have. So I think 10 seconds video is quite enough, good enough to extract the first frequency at least. So I think still we can use this. The second part is most of your example focus on healthy structures for predicting mode shapes and frequency. Yes. So have you researched comparing damaged and undamaged structures? Significant structural damage is usually required to observe notable changes in mode shapes of frequency, which could lead to higher repair cost. Is this method applicable for detecting micro damages? Okay, so coming to the first part. So of course, the first part of all the videos that all the practical examples that I have used is something like where we just go to the site and we try to record that video and try to understand the frequency part. So when you say that compare damaged and undamaged structure, only I can do in the simulation part, whether I should have a good structure and I should damage myself and I have to do it. So otherwise, like, it's quite difficult to implement this in practical case. That's the reason we have used the Toccomanero Bridge and the London Millennium Bridge, where so-called as damage is something like where there is a difficult situation where it has collapsed. At least we could able to extract the frequency. So when it comes to comparing damaged and undamaged, of course, the frequency value that you're going to extract is going to tell you that. Okay, as rightly said, significant structural damage is usually required to observe notable change in mode shapes. Yes, so if there is a significant damage, obviously your frequency value is going to give you that indication, right? So from there you could able to understand that part. So is this method applicable for detecting micro damages? So again, like it depends upon which part of structure you try to record. So whatever we have done for the global monitoring. Suppose, like, I think I have shown a couple of videos for the girder, right? So suppose if you focus on some girder part, if you are more interested in that particular girder part, so then you can at least look into these micro damages. But where you cannot implement this method, but you can implement some other method which I didn't discuss today. We have something called as semantic segmentation. That is also a powerful computer vision method that will be more helpful for detecting the micro cracks. We have detected 3 to 4 different types of damages: cracks, corrosion, spalling of concrete, rebar exposure. Okay, all those things we can do. Is there any method or technique to get crack propagation and rate of propagation of crack from video? Yes, crack propagation you can get from the semantic segmentation algorithm. So where you could able to track the crack, that is possible. So I did not discuss this in today's slides, but that's a different method which a couple of our students are working. So where you could able to get the you see, there are methods where you could able to forecast the cracks. Suppose today in 2024 there is a crack in my beam, for example, let us assume, and if you know the loading condition, etc., in 2026, after 2 years of constant loading, or let us say random loading, or etc., how that crack pattern or how the path of that crack might go. So there are many methods that we could able to do that.
Yes, sir, there is a one question in the chat box.
Okay.
It is asked by Mr.
Chat
NC
box.
Balaji. Yes, sir.
Yes, can you throw some light on, yes, can you throw some light on use of low-cost DAC system and sensors? for such SHM work, how it can be implemented for buildings. Please give some examples on use of such low cost. Yeah, of course, like low cost DAC system where you, of course, we are also using IoT based sensors from where you could able to like manufacture using the MEMS technology, which is quite cheap, right? So where you would able to purchase from Amazon, like you have 500, 600 rupees, you will get 3-4 sensors like ADXL. We are doing those experiments as well. So yes, you can use it, but the problem is that like how accurate is your result? Okay, there comes the issue, right? Because I have used personally, I have used the accelerometer, which is cost of like 3-4 lakhs, like servo type accelerometer for bridge health monitoring, to like as this cheap Amazon based like 60-70 rupees things. So in my lab we have all those sensors. So like it depends like on what is your application, or like what is the range of errors that can be allowed. Okay, so it depends upon that. Of course you can use low cost DAC system provided you try to have the approximation in the results that you obtain. How it can be implemented for buildings? Yeah, you could able to like so we also work on some smart sensors like PZD based sensors. So those sensors can be mounted. You can fix the accelerometers wherever that is required in your building, or sometimes you can also fix the ultrasonic sensors to get the displacement if there is a movement of of the structural member. Okay, you can do that. There is something called as breathing crack. Okay, so when there is loaded, the crack opens, and when it is unloaded, crack closes. Okay, so where we use strain gauge, I mean strain dial gauge for that. So nowadays we can use this ultrasonic sensors. So low cost sensors can also be used. Yes. I hope like I answered the questions whichever was asked.
Yes, sir. Yes, sir.
So,
These are the only questions.
So
Yeah.
thank you so much, Professor, for sparing your valuable time and imparting such a useful lecture on non-contact video bearing model analysis. Really, people attending today must have lot of new things, new technique, new information. So on behalf of Indian SHM Sector Engineer, I thank you very much for sharing your knowledge and experience. And we wish you again to do more and more work for the benefit of the society. Now, two announcements that this monthly lecture, the next monthly lecture would be held on 28th of November. Different topics, different speakers. And the most important is, please note that from 8th to 10th November, we are going to have a national seminar on an important topic in Delhi. Please spare time and do attend for your benefit. Thank you once again, and thank you very much.
Thank you, sir. Thank you.
Yes, sir. Thank you, sir.
Because can we close now?
Yes, sir. Yes.